Okay, hello everyone and welcome. Today's paper discussion that we'll be doing is on GATO. So this GATO is really an ambitious project by DeepMind. You know, DeepMind, their ambition all along has been to create general AI. And this is one step towards that. General AI, for those who don't know, is basically an AI, one single AI that can do many different things, just like humans. Like we can walk, we can eat, we can read books, we can play games. Yeah, there's only one of us. There's no different AI there's like no different AI systems to use whenever we do such things. Okay, so when we talk about this general AI, this is something quite ambitious because you know a lot of the state-of-the-art models right now, like for language, is just like purely for language. Then for example, transformers is meant for natural language processing. Then for images, we have CNNs, convolutional neural networks, recently become transformer-based as well, vision transformers. So that was for images. Then for stuff like sound and everything, typically it has been done using like recurrent neural networks. And then in the end, it became a transformer as well. So I don't know if you all have seen the rise of transformers. Like a lot of different fields start to use transformers because they can model the sequential information without much loss pretty well. Okay, because let me just share with you this thing here. Like the usual recurrent neural network is like that. Like you have a block here, and then you have another block here. This is the hidden state. Okay, the recurrent neural network is like that. Okay, and then you actually have your input here, like at each time step, x1, x2, x3, and then what happens is that this recurrent neural network block processes things the same way. So like this is the hidden state. Okay, I think we should make this like hidden. Yeah, so the hidden state plus the input state will give you the output. Okay. So there's one problem with this kind of architecture is that when we do this kind of architecture, you kind of have a bottleneck. Okay, so the bottleneck actually comes from the fact that you have this hidden state that is supposed to represent everything. So like you look over here, this hidden state here needs to represent all the information that you get before this. Okay, because at every time step, you're only taking this X here and this hidden state here. So the RNN suffers from a bottleneck problem because of hidden state representation. Okay, so what the transformer did, transformer basically they just take all the states at one time and then they do some form of attention. So you do some form of attention over here to get your output. So apparently this kind of architecture is quite useful for many domains. And so this is just a brief introduction why in the end DeepMind used something like a transformer, okay, for this architecture called GATO. Right. Anyway, can you all see what I wrote here? Can you just like maybe give me a thumbs up if you can see what I wrote on the screen?
Yes.
Okay, thank you. Yeah, so this is the background behind GATO. So the question that the DeepMind scientists are asking is, can a transformer do everything? Like you just use one transformer. Can you use that single one transformer architecture to do all your processing? Okay, this is very ambitious. Okay, let us see what this means in the next slide. Okay, by doing everything, okay, this is what it means. It means that you do multi-modal, multitask, multi-embodiment. So these are some of the tasks that the GATO does. Like for example, this first one is something like image prediction. Okay, actually this may not. This one is Atari games. You play Atari games. Okay, this one is Mujoko, some robot tasks. This one is question and answer. Okay, it's like a chatbot. What is the capital of France? Then the data shall reply Paris. This is some simulated robotic arm environment. Okay, this is image captioning. Okay, this is like you get an image and then you need to tell like a cat that is sitting next to a brick wall. You know, nowadays everyone likes to use cats for for their research. Yeah, GATO, in fact, according to the scientists at DeepMind, GATO actually is, I think it's a French word for cat. They got inspired by cats. Okay? So it's really quite a big thing for some reason. All right. Then there's other stuff. This is like a robotic arm, red green block stacking task. Okay, this thing is known as a Sokoban. Okay, this Sokoban is really like when you need to like push boxes to the red color squares, and then this is a puzzle game. Okay, so you need to plan in advance to do this. Okay, and then there's other environments as well. I believe this is some 3D game. This one is probably some, I don't know, some game. I'm not too sure of these environments. Okay, but the idea is that with one model, you can do everything. You can do image stuff, you can do text stuff, you can do games. Okay, so pretty impressive if you ask me. Okay, but at first I was quite impressed. Okay, until I read the paper, then I realized that actually it's still quite far away from general AI. This is really, I would say this is a good beginning. Okay, but maybe we need a lot more before we can accomplish this goal of general AI. Okay, but the idea is you use the same set of weights. You use these transformer weights for everything. So the thing is, you model every problem as a sequence problem. So you are basically predicting the next token given a series of tokens. So this is how it looks like in the GATO architecture. Okay, first, what we will have for GATO is that we will have this like Atari images over here. Okay, so there's a few forms of inputs. So the first input is this. So like you have this Atari images, discrete actions. So you encode them, image is like that. Discrete action is like that. So you can see this is the legend. All right, so we have all this. Okay, and then we go here into the batch input. This is the first stream. Okay, this is for, let me just write here. This is for discrete actions. Okay, then we also have another stream of inputs. Okay, this stream is for proprioception and continuous actions. Yeah, let me use a different color. So this one over here, again, you can take in images. You can take in images, and then you have proprioception. Sorry, proprioception is basically like your joint, how much to move. Like proprioception is like your joints, how to move, what angle, and so on. And then your continuous action will be like, okay, move your right arm by 20 degrees. Okay, so the proprioception is like the state of your arms and your legs of your robot. So you can have this whole thing here as another series of inputs over here. Okay, then we also have other things like text. So text is over here. So if we have things like text, it's like I'm going to London. Okay, then you are supposed to like maybe continue the sentence or something. Yeah, so this will be a text input. So there are different ways you can put the input in GATO. And the last one is the chatbot. Okay, not really chatbot, but this is the image and question. So you have this image thing here, plus the text. So this one over here. And then GATO doesn't predict everything. Okay, GATO only predicts actions, okay, and text. So you can see that if we look at this diagram here, if we correspond it to the back, you can see this this purple thing here. This purple thing here is your action. So for GATO to predict the action, is actually taking this thing here, and then it's predicting on this time step is predicting the next action. So over here is also predicting the next action. Okay, so it is really just a next sequence prediction problem. So at every sequence, you just predict the next one. And for those that are not part of the actions, you mask them out. So for text, what we do is we can also predict the next token. And then like for here, this thing here, question what is in the picture. So maybe the question what is in the picture is this 4 over here. So what is in the picture? Okay, then at this point of time, you're supposed to predict the answer here. So the answer here is like, this part here could be, it's a cute cat. And then this first 4 bricks here is what's in the question. Okay, what's in the picture. So this is the overall GATO architecture. And this is basically a next sequence prediction problem. You have any questions to ask about this architecture? Because it's quite interesting. Okay, they just mesh everything up into one huge array of stuff. They can do everything like images, discrete actions, continuous actions, text, okay, and also question and answer response. And everything is just really just predicting the next token. Okay, so I will go through more in detail in the next one. Okay, I don't want to spend too much time going through this because I want to leave more time for discussion. So the prediction problem, GATO is actually quite smart about it because there's been some work that people try to predict like images, and actually it failed quite badly because images is very high dimensional and it's very hard to predict all the pixels. So instead of just predicting only the images, GATO actually predicts only actions and also text. Okay, so you can see that this, okay, if you all look at the previous discussion video on the decision transformer, so this is like a decision transformer. Okay, decision transformer takes in rewards, state, and actions, and then what it will do is it will predict the next action. So reward state, okay, so actually what this does is that you don't, okay, you given this tree, okay, it will predict the reward state action of the next time step. Okay, or actually in this case, it predicts the, so you can see that the decision transformer actually predicts the next, actually it predicts this tree, but in the decision transformer, they only use the action. So you can see that this way of like predicting the tokens of the next action has been quite a powerful tool, and it has been shown that it can mimic expert performance in the decision transformer. So what GATO did was basically they just used a similar architecture, but instead of putting the reward here, there's no reward at all. Okay, it is really just using expert moves, expert sequences, and then it's just trying to mimic the expert sequence. There's no notion of reward in the GATO architecture. So you can see over here, it is just like observation. It is just stuff like observation. Then we have the action. Okay, then over here is the same thing, observation, and then action. So this action that is predicted, okay, will be like given to the Atari controller and so on. Then the game will be played, the observation will come again, and then you predict this action, and then you can put it back here. So by mimicking like expert gameplay, it is with the hope that this sequence prediction thing can eventually do all domains. Okay, and over here you see that there's this thing called a prompt. Okay, this prompt here is basically supposed to tell the AI what task it is performing, because sometimes it does a lot of tasks and they look quite similar. So in order to do this prompt over here, what they actually did was they actually took samples of the episode and they use this as the prompt. So the samples of the episode is like samples from here. They use it as the prompt. Okay, it's quite a weird way of doing this reward function here, because over here the reward is supposed to tell you like how much total reward you will get at the end of the episode. But what the GATO side does is that it just takes 50% of the time, takes the end sequence of the of whatever trajectory or whatever sequence is following, and then 50% it just uniformly samples in the middle. So this is kind of weird, okay, because it doesn't really tell you what they say that's trying to do, like goal-directed learning, but it's not exactly doing it properly. It's like it's half-half. So it doesn't really, it sounds do goal-directed learning, but I think it is a bit dubious over here, because with just this prompt, like it is very difficult for like even you and I, just from a sequence of observations like that, it's very difficult for us to tell like what game is it or what. If you just take one part of this sequence here, you put as the prompt, okay, it's very difficult for us to tell like what game it is, what task we are doing, and so on. So I'm not too sure why they didn't want to do some form of one-hot encoding. They say that it's not very efficient, okay, but I find that this way is a bit weird also. So this is something we can discuss later. Okay, then also, I think a lot of the inspiration came from here, this T5 architecture, where they actually have a prompt, okay, and a sequence. So the T5 architecture is like a text-to-text one. It's something like summarize. After that, the sequence is like they put a text here. So the thing is like translate from Russian to English. Then you put the text here. So this T5 architecture is like that. So you actually have a task in front. Okay, so this worked pretty well. This is the T5 architature. And over here, this is slightly different, but there's still something like a prompt and then a sequence at the end of it. So this is what GATO did. All right, let me just continue. So this is the way the loss function is structured. So using the chain rule of probability, you have this, like, basically you are given I mean, they are basically trying to do a prediction problem. They are trying to predict, okay, the next token given the earlier tokens. Okay, and we do that for all the tokens. So it is essentially modeling this log p beta function here. Okay, so the idea is basically you look through all your batches of sequence, and then you look through all your index of your sequence, and there's this mask here. This mask here basically is making sure that you are only predicting text or an action, like what I mentioned earlier. And then this one is basically the probability of this target token being predicted. So by actually minimizing your loss here, you are essentially maximizing this. Yours is a negative sign. You are actually maximizing. You maximize the token prediction probability. So actually, this is like a supervised learning problem. You know, when you do supervised learning, you have some form of cross entropy loss towards the end. This is actually, in other words, this is the same as the cross entropy loss for supervised learning. It's no difference. Okay. Goku, you're familiar with cross entropy loss, right? I think your work uses it also. Supervised learning. Yep. Yeah. Yep. Okay. Thanks. So let's move on. So the main thing for this architecture is like, how do you tokenize this architecture? Because there's so many things that you want to encode into your model. So there's a few modalities. So over here you see there's text modality. So for text modality, we have this sentence piece that is used quite well in natural language processing to like split a text into subwords. So sentence piece is used with 32,000 subwords, and then we order them with the index 0 to 32,000, not including 32,000. Okay, then I bring your attention to the last point here. The last point is this continuous values. Continuous values here is also, okay, it will be mu law encoded. So they do some exponential encoding using the mu law, and they basically discretize into 1024 uniform bits after that. And then they actually shift it down to this index here, 32,000 to 33024. Okay, then the rest of them, the rest of the stuff is images will just be like between -1 to 1 and divide by square root of patch size. Okay, this is for image, and then there's also discrete actions. Okay, it's just from 0 to 1024. Okay, the main thing is it is all tokenized into indexes, and the index later on you will see that we actually use this index and map it to some form of dictionary. So this is the idea. Each of them will be encoded differently. Okay, so this is the one from the paper. So we basically encode all the observations in time order. Text is the same order as the raw input text. Image in raster order, which means like row and then column. Yeah. So I mean just row, raster order. Yeah. Then the tensors is row major order. Yeah. This is the default TensorFlow one. Okay. After that, we concatenate all of the tokens together into one mega sequence. So you can see it's very complicated. One full length of episode consists of everything. Like you see this Y, you have the text, you have the image patch, you have tensors in basically the discrete and continuous observations, and then you have like your actions. So every single episode contains all this. Yeah. So there's a lot of things that is encoded here. So this whole thing will be encoded into the network. Okay, let's move on. So we then need to embed this into a form that that can be done with backpropagation. So the main thing to note is that the text, discrete or continuous value observations are embedded into a lookup table. Okay, later we'll see an example of how this lookup table is used. Okay, then we use the image patch, okay, using a ResNet to encode. So this image patch, also you have a vector per patch that is encoded with some form of ResNet encoding. So this is using some form of technique that is very similar to vision transformers. Okay, and then other than that, see, it's so complicated. Other than that, we still have another embedding here called learnable position encoding that can actually add, like based on that position, you add some vector to let the network know, okay, this is like position 1, this is position 2, this is position 3, and so on. Okay, let's continue. Okay, I will show you all the, okay, I'll show you all the images. I think easier to understand from this slide. So you can see that this is the image embedding. Over here, we actually have, okay, like a network like this. Oops. If let's say we want to do image embedding, they actually split the image into like 16 by 16 pixels. Okay, and then at each patch, okay, you will get the X and Y coordinate to get the relative position. And basically you have this row and column embedding. So your column will have a certain vector, your row will have a certain vector. Okay, and then after that, your ResNet-based embedding is basically saying that, okay, you feed this patch of data inside, and then out comes a vector. So it's very complicated. I personally don't quite like VIT because I feel this kind of is not exactly the most efficient way to process images. Okay, I mean, there's a paper that actually showed from NUS, I believe, there's a paper that showed that VIT, you need to train on more data in order to be competitive to CNNs. CNNs can actually learn better with fewer data. So yeah, this is the way that they decide to use it. Okay, using VIT, vision transformer methods to do image embedding. Okay, using basically a patch embedding plus position embedding. Okay, so this is for images. Then we also have this for, what do you call this? For image plus discrete actions. So if let's say we were to do the images, okay, it's basically just now the same embedding that we saw earlier. This is for the VIT. This is basically VIT embedding. Then other than that, we also discretize our image. And then we have an embed table. Okay, this is basically the embedding layer in TensorFlow. So this basically maps an index into a dictionary. Okay, after that, what we do is we then concatenate all these things together. So this part here comes from the image. Okay, this part here comes from here. This part here gives rise to here. Okay, and then we have another part here that comes from the discrete action. Okay, and then we also need to add in local position encoding. This one later I have a slide to show you this. But the idea is you concatenate your image and your action, and then out comes the sequence. So this is how the sequence is embedded for image. Yeah. So for proprioception and continuous actions, it is a very similar process. So the main thing is we first need to, instead of processing it like a vision transformer, we first need to use some form of proprioception encoding. So over here, they use the mu law encoding. Okay, I don't have the equation here, but you can look at the paper for the equation. So basically discretize into 1024 bins. And then at each 12024, you actually pass it through an embedding layer again. So basically you map the index to vector. And this mapping is different from the previous mapping for the discrete action. Okay, this is the proprioception embedding. So you actually have an embedding for this. Okay, then for the continuous action, you also have another embedding table. Okay. So there's a lot of embedding tables that are used over here. And then after that, we concatenate. After we embed into a vector, we concatenate all of them together. So like again, this 4 comes from the proprioception, and then this one comes from the continuous action embedding. And then now we add in the local position encodings, which will be shown in another slide. And then we get this whole sequence like that. Okay. You have any questions so far for all this tokenization process? Okay, or is okay? You understand this? Okay, it's really just basically encoding everything into vectors. And these vectors will then be used for prediction. So what is this local position embedding? So this slide talks about it. So the local position embedding is like this. If let's say we have the original token as such, okay, and then we know that this is index 0, 1, 2, 3, 4, 5, and so on. So you actually can embed a learnable position embedding here. So this one again learn through backprop. You can learn through the weights. You add this position embedding. From this vector here, you add this embedding, and then you get this thing here. Okay, so this is really end-to-end learnable. Okay, I myself don't agree with the learnable position embeddings. Later you see in the discussion question, because I feel like this means that you cannot generalize very well, because if you like learn a specific kind of embedding for certain tasks, like what makes you so sure that this embedding is like, maybe this learn embedding encode some task specific stuff. So I really don't feel like local position embedding is the way, because the original transformer also didn't use learnable position encoding. They just use the sine and cosine kind of waves in order to encode the position, which I felt was better. Okay, because like one thing is neighboring positions here. If you take a cosine, you do the attention thing. In the original transformer, okay, the neighboring tokens have high similarity. Okay, but further tokens, low similarity. Okay, which is very important, okay, in order to tell you like how close a certain token is to affect another token. But if we do learnable position encoding, we lose out this similarity metric, which I feel will hinder generalization. Okay, so this is just my point of view. Okay, then there's another thing called action embedding. So this thing, action embedding here, regardless of position of where it appears in the sequence, the action embedding is always going to be the same vector. Okay, so why do they do that? I have a feeling it's because of this. If you were to use different embedding vectors for the actions, then there will be some form of bias incorporated to your action that is not related to the action itself. So like your action token here can be biased by your embedding and then become something else. So in order to make the bias the same, they actually use the same local position encoding. And I believe this highlights why this is important, because of this similarity thing, is not able to capture the right associations. Okay, so I have my doubts about how this local position embedding is done. Okay, I mean, I really think that they should have just used the original transformer way of doing it, where you just take a sine and cosine wave, okay, in order to have this thing here. Okay, so that's it for the thing. All right, so this slide here, I just included here just to show how difficult it is to train this architecture. So we do have this, they actually mentioned that in order to train this architecture, hi Rishabh, in order to train this architecture, the hardware used is basically just 16 by 16 TPU V3. So I just put this thing here to just show you. If you really want to train this, okay, they actually use a batch 512, and you see the token sequence length is 1024. So the tokens is what I talked about earlier. You have all these observation tokens and so on. Okay, you put the learnable position embeddings, you have all this thing here. So the token length is really this one. So like the total number of tokens here with the full sequence concatenated together. Okay, that token length here is 1024. So it's quite a lengthy token length, but I don't think it can really go through a very large part of the episode, because you see, if we look at the original diagram here, when we do the embedding, you can see that if we split the like one episode like that, like for example, Atari image and discrete action, you have an image come over here. These already 2 tokens, okay, or even more. I mean, here they show 2, but it could be even more tokens. This one is 1 token, and then this one 2 tokens. You can see that just to encode like maybe one state, you need 3 tokens already. So token length of 1024, maybe, I don't know, 30, okay, maybe about 300 sequence. Okay, maybe that's far enough to encode quite a long sequence, but it's just 12024 tokens. Yeah. So yeah, the idea was just to, let me just go back. So you can see that they took 4 days to train with so much hardware. All right, so if you were to calculate how much it costs, you can calculate yourself, like 32 core instead of 8 core is like they use 16 by 16 over here, so it's like in the middle. Yeah, it's quite expensive. Yeah, so nowadays deep learning architectures really need money to train. Okay, so this kind of experiment, must thank DeepMind for doing it, because I don't think any of us can actually afford this amount of compute right now. All right, so what are the data sets used for GATO? So for GATO, they actually use a few data sets, and basically they use quite a lot of popular data sets in the past in order to do it. So there's like game data sets like Atari. Atari Extended is basically with some form of randomness in the game where you have different objectives. So they created a few environments for this. DM Lab is like the robotic arm lab. Sokoban is the push the card into the square box, into the square region. Baby AI is some kind of using text to give you the task, and then you need to perform the task in a 3D world. Yeah, I think it's a 3D world. Haven't seen this before. The DM Control Suite is all the robotic arm control. Okay, there's a few like meta words like 3D stuff. PropGen is also 3D environments. RGB stacking simulator is DeepMind has this robot that they can have a robot pick up some bricks, so the bricks are in red, green, and blue color. So this was discussed quite a lot in the experiments. Okay, modular RL is basically a Mujoko environment where Mujoko is a physics-based robot like simulation. So modular RL is an environment where you mix and match the body parts, and then you are supposed to work. I mean, different configurations of the robot, you still need to work in the environment. Okay, and so on. I mean, these are some other DeepMind environments that they use. So total of 596 tasks here, and then they also use some text tasks, massive text from the internet corpus, MS Coco captioning, question answer data sets, and so on. So it's really quite massive. And you can see over here, this is the sample weight in terms of when learning the architecture. Most of the weights you can see are biased towards this kind of 3D games environment, and then only like 15% of the weights are for text. Okay, so this is the idea. Actually, some of these texts can also help with some of these environments here, especially for those who use text as input, like Baby AI. So it's quite a massive collection of data sets. So okay, this is the thing about GATO. Okay, at first I was quite impressed with it. Then I realized something. It's similar to decision transformer. They don't actually generate the trajectories themselves. They actually learn from someone who has mastered the game already. So they're already learning from expert trajectories, from SOTA or state-of-the-art or near state-of-the-art agents. So they only select the episodes where the returns of the episodes are 80% of the expert return. So it's training on the good episodes only. So it's quite different from decision transformers, where you can actually train on different kinds of episodes. Okay, let me just write this down here. Decision transformers, you can actually train on all kinds of episodes. Okay, because we have the goal as total reward gain. So you can actually learn from good, from bad episodes. But for this GATO architecture, you can only learn from like the good episodes. Okay, because GATO does not have any form of reward model inside the sequence. It's just observation section, observation section. Okay, the only kind of reward that they have is actually the prompt, as I mentioned earlier. This, where is it? This prompt over here, which is randomly taken from the sequence. Okay, this prompt over here, randomly sampled, or 50% from the N, which tries to serve as goal-directed learning over here. Okay, I have my doubts about this. Okay, is very different from decision transformers because it does not have this kind of goal explicitly embedded inside. So what they do, they only use good episodes. And is this restrictive? Yes, okay, because I think for learning, you not only need to learn from the good stuff, you also need to learn from the bad stuff. You need to learn how to avoid those bad stuff. Right? If you only know how to replicate the good stuff, when I throw you into a random starting point that is near the bad zone, you don't know how to go back to your good zone because you haven't seen this kind of observation before. So I think this will lead to a weak performing AI, okay, if the environment is stochastic. Okay, the only reason why it can be good is that if you train it with so much data, you start from good, from bad, with the expert trajectory, yes, then you can learn. Okay, but if not, this is a fundamental problem with GATO. Okay, it only learns from the good things. Okay, it doesn't have the bad experiences to learn from. And then they say that it's supposedly possible to use this architecture to learn reinforcement learning from scratch. A bit hard. You look at the amount of data they use to train this. just from expert trajectories alone. If you were to repeat this from scratch, okay, it can take quite long. Okay, I mean, especially each environment can really take days to learn. So I have my doubts whether reinforcement learning can really learn this from scratch. Okay, I mean, especially when you only model the extrinsic rewards, okay, which is the environment rewards. Okay, it's been shown that in a sparse setting, it takes very long to learn. Okay, so maybe we need to do intrinsic reward modeling, okay, which is something that I'm quite interested in nowadays. Okay, so I have my doubts whether this can actually learn reinforcement learning from scratch. I don't think it can. I mean, I'm ready to be surprised, but I don't think it can, because of the way it's trained. It's just mimicking expert trajectories. It's not even as versatile as decision transformers. Okay, but the good thing is that they do on a lot of tasks. So you can see that this actually is a stretch test to see how many tasks can an AI model. So let's see the outcome of the task. Is the general agent as good as the expert? So they learn from expert trajectories. Are they as good as the expert? So you can see, like for here, the Sokoban is here. So the percentage of tasks as a threshold of expert score. So it's like over here is like, if you can do this task, like how many tasks are there that can match 40% of expert score and so on. So like this top part here, I think it's Sokoban. Not too bad actually, Sokoban. That means Sokoban, the environment is similar for most of the time. You can match the expert score quite well. Okay, the worst environment that you can see here, y'all can see what's the worst environment that doesn't match the expert that well. Okay, so over here, this is the total number of tasks above threshold. It actually need not mean that it's bad. Okay, it just means some environments have more tasks. Okay, but you can see over here, okay, so what we should be looking at is actually the gradient. Okay, not so much the number. Okay, so actually DM lab performs quite well. Maybe DM lab is more constrained. Actually, what I said earlier, the Sokoban is actually the worst performing, because Sokoban has the steepest slope. It means that most of the episodes didn't reach the expert score. Okay, maybe did quite well, maybe at 40%, but it doesn't reach the expert score later on. So yeah, Sokoban is the planning one. So it means that it doesn't really do planning that well, which is understandable because there's no planning involved in the model. It's just a sequence prediction problem, a model-free problem in reinforcement learning terms. So you can see that like there are some environments that are easier. I think all this DM control suite, all these are not bad because maybe they already simulate with all kinds of possible interactions. Okay, the harder environments are like maybe pixels, DM manipulation playground. This red color is Atari. Atari is quite difficult. Atari extended also quite difficult. Okay, understandable because Atari is very sparse reward sometimes and it's very difficult to learn. Okay, I mean, if you all play Atari games, if you don't know the rough concept to play it, you learn from scratch how to play it, it will take quite long. Okay, so yeah, any questions on all this so far? So you can see that the there's really a lot of things that that don't perform as well as the expert score, but most of them can achieve like maybe 20% of the expert score. It seems pretty good. Yeah, so it shows that there's some form of learning. There's some form of imitation. It's just that it doesn't imitate that well. So like you see the total task here, and then the total task that reach expert score varies based on environment. So the question we ask ourselves is GATO scalable? Can we scale GATO to perform even better? And the answer is actually yes. So what they did was they actually did this mean normalized score. So what is mean normalized score? Performance of the model as percentage of expert score. And then after that, you average this percentage score across all the tasks across of a domain. So this is needed because one domain can have like maybe 38 tasks, different tasks in like maybe a robot manipulation. You have different things you can do with the robot. After you average across the domain, then you mean aggregate the percentage score across all domains using the weightage that we've seen earlier, that weightage in all the data sets. So the main thing you need to take note from this graph is like this. So they did GATO with different, okay, we do the tokens first. So the more tokens processed, which means the more data set they use. Okay, the more they use, actually, at the beginning, there's a huge improvement. Okay, linear performance like that increase. After that, it tapers off. Okay, it becomes about a log performance, log linear performance like that. Yeah, so it means that I think if you follow the trend like that, it doesn't look like it will reach 100%. Okay, it will probably taper off here. And that may be because it only models the good stuff. It doesn't model the bad stuff. Okay, you can also see another thing, increasing model size. As we increase the model size like that, you realize that you actually gain performance increase. So you can see that there's a performance increase if we go up like that. And that is something that is quite interesting, because this means that we are able to scale up the model and gain some performance gains. Okay, but again, you see over here when we scale up the model, do you notice something? You see over here 79, 79 to 364. You can see a big jump here. Okay, and this is only about 300 parameters, 300 million parameters. Okay, can y'all see that from the 364 mil to the 1.18 billion? This is about, I don't know how many million, about 700 million, right? Can y'all see that, that we actually increased the model parameters by more than 2 times? Okay, but the performance gain is like less than about half of what you gained before that. So I don't know. I leave it to you to interpret this graph, but my understanding is scaling won't lead us there. Richard, what do you think? You look at this graph, you think if we increase to like 1 trillion, do you think we can get expert performance?
I don't think so.
Yeah, I don't think. Who here thinks that we'll get expert performance looking at this graph? I let you increase the scale all you want. I let you increase the number of tokens processed all you want. Can we achieve expert performance with a GATO-like model? Okay. How about the rest? What do y'all think? Yes or no? Like this one.
I don't think it's an issue of model capacity, as in like just because we make it double the billion size or even trillion, it might even how do I put it? It won't generalize. I don't think it'll generalize just because we increase the number of parameters.
I agree. Actually, the more you train, actually sometimes you get a negative performance after that.
Yeah, suddenly after a while. Yeah, suddenly after a while it just decreases.
Correct. So I think there's something missing here, and the missing stuff is maybe what I described earlier. The position embeddings, learnable position embeddings may be bad. That's my hunch. Okay. The other thing is just merely predicting the sequence without doing any planning. Maybe that's bad. And I think the key thing that like irks me is this part here. You only train with the episodes that are good. So it means that you only learn the good stuff. And people have done experiments on like behavioral cloning. You know, if you just train on the top few behaviors, it's not good enough to learn everything. So I think this is the key reason why GATO is not very well. But then again, I believe they did this because of training feasibility. If you use all the returns, maybe it will take too long to learn. Yeah. So yeah, that's my thoughts on this. Okay, I'll move on. Okay, so actually I have a discussion section later, so we can talk more later. Let me just finish like the last 2 slides. So the key thing to find out is, can GATO generalize? Okay, I'm not too interested in whether GATO can fit the training distribution. Okay, because it's quite easy to fit the training distribution. If you do neural networks, you realize that neural networks will fit the training data as good as they can. Okay, but the thing is, can the neural network generalize beyond the training data? That's the $1 million question. If you can generalize beyond the training data, you can use it in the real world and you can learn new things. Yeah, but can GATO generalize? Okay, that's the key question we'll ask ourselves. So over here, we use the DM lab environment. They use the DM lab environment here. And over here, you can see that there's a few different objects you can choose from: polygon, trapezoid, parallelogram, and rectangle. And then they basically held out 3 sets of triplets. Okay, that are not. So maybe this object can be seen before, but in this set of triplets, okay, it's not seen before in this configuration. Okay, out of this set of 5 held out triplets, then they evaluate whether. Okay, so in this case, the idea is, I believe, to stack the red on top of the blue. Okay, it's one color on another. I forgot what color on what, but the idea is you need to stack one color on another, based on the what you give here, the different shapes. This is in the DeepMind lab. Okay, they have this robot here. This I think costs a few like $10,000 for this robot. Yeah. So this is the task that the robot needs to do. Okay, so we look at the in-distribution data where basically they train with the triplets as well. So you can see with the in-distribution data, like GATO actually in distribution, okay, there's some thing to qualify here. Okay, in distribution means that they actually seen this shape before. Okay, but maybe not in this configuration. Okay, out of distribution means that they have not seen this shape at all before in all these triplets. So there's some difference. Okay, in distribution is a bit more relaxed. And you can see that GATO actually performs not too bad for the groups. Okay, you can fancy a guess why group 5 works better, I guess, because this one easier to put on. Yeah, I mean, you look at this blue shape here. It's so hard to put this on. You need to like top. If your agent just put this on top here, you will likely fail. You need to like sort of angle the trapezoid in some manner. Yeah, so yeah, there are some reasons why it doesn't perform so well, but overall it's not too bad. I mean, it's about the same as behavioral cloning. Okay, but the key difference is the out of distribution data. It does horrendously poor. You look at this. Okay, I mean, DeepMind said that they did not bad, but if you look at it, it actually doesn't look very good. Only maybe group 4 did quite well, but out of distribution data, it doesn't generalize that well. But I have to give it to them, but it can solve like more than half of the time for some groups. Okay, so I think zero-shot transfer is still a problem for GATO. It can learn something similar, but it may not be able to generalize zero-shot. Okay, and this is actually not just a problem for GATO. This is a problem for machine learning in general. Okay, this is quite ambitious. Zero-shot generalization is very ambitious. I mean, my research paper on the break tic-tac-toe, I tried to generalize zero-shot. I also realized it's quite difficult. You need to really give it a lot of different environments. I use domain randomization before it can do zero-shot generalization. And so the more complicated the domain, the more kind of varying examples you need to give it. Okay, I found that like if you do like increased search, because I use some of model planning using AlphaZero, if I increase my search depth, it actually doesn't generalize zero-shot that well if it hasn't encountered a variation of that scenario. So zero-shot generalization is like the holy grail of machine learning. We have not reached it. And so it's expected that GATO doesn't do well in it as well. Okay, so now maybe we should relax the question and ask ourselves, let's do a few-shot generalization. Okay, so few-shot generalization, okay, ideally we should learn how to condition on different prompts. Okay, like for example, learn how to, based on the different prompts, you know how to generalize to a new environment. Okay, but however, as what I mentioned earlier, the prompt is just a random section of the sequence again, which is not a very good way to do prompts. Okay, so this leads to some hard to describe things because your context length is, okay, this context, not content. Context, your maximum context length is insufficient to describe the task. Okay, so instead of doing conditioning by prompts, okay, what was done is instead, okay, we actually let the agent learn a bit of the task. We actually fine-tune the agent on the task. Okay, and we evaluate the fine-tune performance. Oops. Okay, this is my second last slide before the discussion. So fine-tune and evaluate the fine-tune performance. So there are three different things that we will compare later in the next slide. So one is same domain only data, means you only pre-train from data in the same domain. So all these models here, okay, the pre-training data doesn't include the experiment we are testing on. Okay, but we can pre-train on similar environments. So like same domain means like if you are testing on the Atari boxing game, I can pre-train on all the Atari games except the boxing. I can pre-train on Pong, Breakout, Sequest, and so on. Okay, no control data means I don't even pre-train anything. If let's say it's an Atari game, I cannot pre-train on Atari games. I have to pre-train on text, on image data, and so on, but I cannot do anything for Atari games. And then we have another model called Scratch, which means no pre-training at all. It's like really just train from basically you take the model and then you just, your fine-tune is your training. You train from scratch. So let's see how the few-shot experiments work. So there are 4 experiments that are reported. Okay, the first is a cup hole swing up, is a dynamic control environment. Here you can see the aim is to swing up the cup hole by controlling this blue color platform left or right. Okay, we have meta world assembly, which is like this robotic arm simulation. And there's this task called assembly. I couldn't find the animation for assembly, but there's a task called assembly v2 that is used, like maybe to assemble a cupboard or something. Yeah, so I'm not too sure what this task is, but it's from this meta world package. Okay, there's this DM lab where they have this 3D environment. Like if you all played Counter-Strike or you play modern 3D games, it's like you control a player and then you need to pick up some objects. And over here, you need to pick up apples. Okay. And then lastly, we have Atari boxing, where we have these two stick figures here and we try to box each other. Okay, so what are the results of this few shot fine-tuning? So the results are like this. So for non-image data, so this is proprioception data, where you only have the state of the joints. Okay, and this also is proprioception. Okay, the non-image data, okay, when they actually did this experiment, so with no control data, which means that anything that is not in that domain, okay, it doesn't give much benefit from scratch. In fact, it might even hurt the performance, okay, because you taint it with other things that are different. Okay, if we do not have the right proprioception data, no use training on other data. So this is what they found out, okay, which is quite interesting. Okay, it means that maybe when we want to do like proprioception, we really need the right body to do it. Okay, we cannot just use any body to train it. Okay, or maybe they just don't have the right environments to do transfer learning for that. But the idea, what we found is that there's no transfer benefit for non-image data. Okay, but how about for image data? I keep pressing the wrong button. For image data, this is what happens. For image data, if the image is natural, like this apple can be found in like ImageNet, can be found in the MS Coco captioning, okay? You can actually see that with just the control data, which means no control data, which means I don't use this environment at all. I just train on like image captioning. Actually, it might help the agent recognize that this is an apple. And so you can see the performance is much better than from scratch. Okay. But for Atari boxing, even if I do some pre-training from like ImageNet and stuff like that, you see that the control and the scratch is in fact very similar to using all data also. I mean, so this means that actually Atari games, the images don't look very natural. There's no transfer value. Okay, and also it also shows that Atari is not very well reflective of the real world. So if you want to do like real world planning, you shouldn't use Atari. Yeah, because it doesn't work out too well. Okay, so yep. So that's the end for this. So yep. So we move on to the discussion section. Okay, so yeah, just feel free to chime in if you have anything that you want to add. So the first thing is like in this GATO architecture, they use CNNs instead of vision transformers for the image representation. So what do you think is better to use to like process images? Anyone want to say your view? Like my view is that CNNs are better in terms of generalization, because using the right using the right bias of the filter, you can actually like map this filter to like larger objects. Yeah, rather than just like putting the image to patches, and then it may not be that generalizable. Yeah. Do you have anything to add on this? Evan, Goku, or Li Shuo, you like based on your experiences elsewhere, do you all have any idea on like which could be a better representation? Yeah, so it's okay. Yeah, no problem. I mean, I can just go through this. If you have anything, you just feel free to add. Okay, then the second thing is about this learnable position embeddings. So this one is something that I feel that they did it wrongly. Okay, we should actually use the predefined embeddings. Okay, because the predefined embeddings, okay, have higher similarity for nearer tokens. Okay, which is something that helps to boost generalizability, I believe. Okay, so yeah, if you have anything to add, you can just say. If not, I will just continue. So then there's also this next thing is called they actually have difficulty generalizing without the fine tuning. Okay, so this is basically how can we better encode this context in the prompt or network structure. So remember earlier on we have this prompt that is quite random, and then basically they just take a random sequence or the end sequence. We have the prompt, and then we have the sequence. This is the sequence over here. So this is quite interesting because this prompt over here, okay, this prompt over here came from the sequence itself. So, I mean, if you ask someone to learn a new task, and then instead of describing the task to him, you just give the person like, okay, this is another part of the task you will see later on in your life. You will see this is the right sequence. Kind of weird, right? I mean, the prompt shouldn't be the sequence itself. I think it might be better to like maybe have to find a general way to structure the prompt. And this general way can be like in terms of like maybe categories, like maybe proprioception, like text, image. I mean, you have to find a way to make the prompt such that, or maybe you can just describe the task in text. Yeah, because I mean, if T5 Hello, sorry, just now my computer ran out of battery. Goku, did you all get logged out or was the session still ongoing when I left?
It was ongoing. It just you just left and you joined back. Hello. You can hear me, right?
Oh yeah, Goku, did the session break when I left or it was still ongoing?
No, it was still going. It was still going strongly.
Evan, are you there? Okay, I guess y'all could y'all were still in the session, I believe. So let me just continue, okay? Yeah, okay. All right, so basically what I wanted to say is that we have this prompt network, okay, that we actually failed to, like, instead of using just the prompt sequence, okay, we actually don't really want this thing, okay? We maybe want to give the prompt, okay, maybe we want to give the prompt like a text input, okay, and this maybe text input can describe the task. Okay, maybe this would be like more generic than the way they actually structured the prompt in GATO. Okay, so this is something that I was thinking of. If you have any suggestions, feel free to let me know as well. Okay, then there's a second point of questions that we can ask ourselves. And one thing is, GATO never seems to be able to beat the expert. Okay, why? I mean, to me, I feel like this one seems to be like more of a explore exploit thing. Because if we just like learn to mimic, if you learn to mimic, you don't really learn everything. Okay, you only learn the good stuff. So especially in this GATO, they only learn the good experiences, 80% or more return. So this means that it need not be able to explore the search space completely. Okay, unlike a lot of other algorithms like Monte Carlo tree search and so on, where you actually do explore and exploit. Okay, but this may be infeasible in very high dimensional state spaces. You may not be able to explore everything. So I think it's understandable that a general agent will necessarily be poorer than the expert agent, unless you can do some form of transfer from one domain to another domain. Okay, so the other thing that I was thinking of is GATO is more or less model free. Okay, like decision transformers. Okay, so maybe it will be better to include a world model for planning, and this world model can be very simple. Okay, you just be like predict next observation from current one, and this can be done with a transformer as well. Okay, but instead of predicting the next observation, maybe you want to predict next hidden space representation. Okay, basically this is the idea of abstraction. Instead of predicting the original diagram, like for example, you want to predict my face, you see the tree moving at the background over here on the screen. You maybe don't need to depict the moving leaves of the tree if the task is just to predict my face. So you can actually zoom in on a very, very focused view of what you need for the task. And that is something like what Yan LeCun was proposing in his new vision of AI systems. You can actually use this to predict the things that are relevant for your tasks. So I believe some form of transformer or sequence-based method could be used to do some prediction of the model. Okay, I mean, the other way to do this model is to actually do a Markov decision process. Okay, but I think this is not intractable for high dimensions. Yeah, I don't think it's possible to use Markov decision process because it just takes too long, okay, to learn. So this kind of sequence predictions, I think it is helpful. So the last question I'd like to ask is like, do you think GATO can learn from scratch, like from AlphaZero? So use an AlphaZero-like method where you learn from itself, from self-play, or like learn from past experiences and improve itself. Okay, maybe it can learn. Okay, maybe it can learn. You have experiences over here that you generate from your. So maybe you have your agent. Okay, so you have GATO. Maybe this is your agent. Okay, your agent generates the experience through the environment, and then you use this experience again to train the agent. Okay, so possible to use self-generated experience to train itself. Okay, but the problem is might end up in a small section of the state space. Okay, because you actually only experience things that your model predicts. Okay, there may not be sufficient exploration, and so there may be a need to include some form of exploration mechanism in the experience. So you could do like maybe like epsilon greedy, where in a epsilon amount of time, epsilon proportion of the experience, I take the best action, which is the model action. And another 1 minus epsilon, I'll just take a random action or take an action by another policy. So it is possible to use this kind of exploitation, but there's a fundamental problem with the GATO architecture. Okay, because it doesn't have any rewards. Okay, no rewards. Okay, means no way to benchmark goodness of experience. So maybe there needs to be a way to tell the model. You need to model in the rewards. Okay, so maybe you need to model in your rewards, and this is the problem. Okay, because if you were to model in the rewards, you need to have some way of making the rewards scalable for all domains. Okay, so this this is some problem that needs to be tackled when you want to do this kind of general agent. You need to scale the rewards maybe like -1 to 1. Is there a way to model intrinsic rewards? Yeah, I think this is important as well, because intrinsic rewards can help to guide exploration as well. Okay, so yeah, I think that's more or less what I have to share for today. Yeah, thanks for attending. Do you all have anything you want to add on to the discussion? Okay, yeah, if not, thanks. I'll see you all next time. And yeah, see you around. Okay, bye-bye.